this part we are going to define what is thermal resistance, and we'll see how this resistance is almost similar to the electrical resistance, and then we'll try to use that similarity in solving the questions also in the series combinations and the parallel combinations as we saw in the electric current chapter. So let's start and see how we are going to apply this. Now let's start the combinations of the conductivity through a very common phenomenon, which are the series and the parallel ones, which you have seen in current in your classes. Here we'll see what happens if we apply the same kind of concept, we extrapolate it to the conductivity in case of rods. That is, in this case here it's the conduction of heat, in the current it was the conduction of electrons. So they are almost similar, so we'll see how far the similarity goes and how we can solve this using this method of series and parallel combinations. Now what is thermal resistance? Is the first thing. Now if you remember, the formula that you had is this. dt by dx, right? We write it like this. dx by k into a minus, okay. Now what is this delta q by delta t? Is the rate of heat flow. We consider this as the current. The heat current is I. This is dt is temperature difference. If you write it higher value minus lower value, so it will be a positive one. So in that case it will become current I is delta t by, I denote this whole thing by R, delta t by R, where R is dx by Ka, where dx is the length in which the temperature is changing by delta t. So if you consider a finite length, maybe smaller, L by Ka. This term is L by Ka. It has been given the name thermal resistance. Why this is so? This is because now this expression is similar to your Ohm's law. If you remember, I was V by R. What is V? V was the potential difference, that is delta V. In this case, that potential difference is temperature difference, and whatever else is there, that was the resistance in there. It's called the thermal resistance here, and here this is the flow of electrons. In this case, it's the flow of the heat. So these two are quite similar, and in this case, the resistance becomes L by K, where L is the length, K is the conductivity, A is the area of cross section. Now let's see what happens in a series connection of rods. Now suppose if you have a series connection like this. Now then you have a different rod here. Okay, these two are connected. Suppose this is temperature T1, this is T2. Now the idea of the series is same when it's connected in this manner, such that in that case there the current was constant. Here also the current is constant. But what is the current here? It's the heat current. So if it's connected in this manner, that the heat current is a constant, it is a series connection. So like if suppose this is made, it has a resistance R1, this has a resistance R2. What is this R1? This R1, suppose I gave this area A1 and length L1. Its length is L2, area is A2. That means what is R1? L1 by K into A1. I am assuming that they are made of the same material. If they are made of the different material, that value of K will be different. So you will have K1. Okay. Now the second resistance here you have is R2, which will become L2 by K into A2. Now this K, the thermal conductivity, it may be same or different. We are assuming here as the same values. So that means it's K into A2. Okay. Now since they are connected in series, what is constant here is the heat current. So what we do is that we equate the heat current for both of these rods, right? Now for the first rod, you will have the heat current I, that is delta Q by delta T. It will be temperature difference is T1 minus T. What is this temperature T? T will be the temperature at this junction. I assume that this temperature is capital T. So the temperature difference here is T1 minus T by R1, where R1 is the thermal resistance of this first rod. Then this T1 minus T becomes R1 into I. Now we find out the current through the second rod, that will be T minus T2. T is the temperature of this junction, T2 is the temperature of this end point. That means the temperature difference is T minus T2. So you get the current is T minus T2 by R2. Now what we know here is that since this is a series combination, the current will be same, right? That means we equate these two current. If we equate these two current, what we have here is this T1 minus T2, it becomes R1 plus R2 into I, right? That means the current I is T1 minus T2 by R1 plus R2. Now if we consider this system as one, so that we can find out an equivalent combination, that means we consider it like a single rod that has a temperature difference same as T1 minus T2 and a length of L1 plus L2 and some resistance R. This value of R will be given by R1 plus R2, as is evident from the solution that we made it here. So the two rods together is equivalent to a single rod of thermal resistance R1 plus R2. So what will happen if we have n number of rods in series of different thermal resistances from R1 to Rn? We'll have simply R1 plus R2 plus R3 going to Rn. So if you can see, this is very similar and identical with the one we saw in the current. So this idea of series combination can be extrapolated to the thermal currents. Now let us see what happens when you have a parallel connection of rods. What will happen in parallel connection of the rod? It's very similar to again what we did in the current. Here what will be constant is the temperature difference. In there we had constant was the potential difference. In this situation what is constant is the temperature difference, such that the temperature difference is same. So now it could be like this. These are the two rods. This whole end is at temperature T1, this rod is at T2. Now this has a resistance R1, this has a resistance R2. Now both of these rods, they have same temperature difference. That means they are in parallel. And what is constant in this was the temperature difference. So again I apply the same thing here. The current through the first one is I1, that becomes delta Q1 by delta T. So if I assume that current through this is delta Q1, this becomes T1 minus T2 by R1. T1 minus T2 is the temperature difference by R1. That's the first for the first rod. Then you apply the same thing for the second one, delta Q2 by delta T, T1 minus T2 by R2. Temperature difference, if you see, is constant, same in both of this, right? Because they are in parallel. What is the total heat current going? Total heat current is, if this is delta Q1 and this is delta Q2, total heat current is delta Q1 plus delta Q2. So if I want an equivalent system of this, equivalent system means a single rod of resistance R, temperature difference T1 minus T2, then what will be this value of R? That's what a equivalent system means. So for this, what again I can write is that delta Q by delta T, small t, is T1 minus T2 by R. So what I do is that, now this delta Q is delta Q1 plus delta Q2 by delta T. Now I need to find out this value of R, so I will equate this with these two values that I have and then try to find out what is this R. So what is the total heat current? I1 plus I2, it becomes T1 minus T2. This, you take this common, you have 1 by R1 plus 1 by R2. This expression, I is equal to T1 minus T2 by R. It can be written like this. So if I equate this, what is the value of R? 1 by R1 plus 1 by R2. So again you see, it's again similar to the current theory. So this is 1 by R is 1 by R1 plus R2. What will happen when you have n number of the rods connected in parallel? Then you will have 1 by R1 plus 1 by R2 going to 1 by Rn. So you can see it's very similar. So you have to use this portion, this theory that we have studied, and apply it in solving the question. So let's see this question. A cylinder of radius R made of a material of thermal conductivity K1 is surrounded by a cylindrical sheet of inner radius R and outer radius 2R. So you have this, and then you have, it is surrounded by this of radius 2R. This is 2R. Okay, and what is the inner radius? This is R. Okay, now first has a thermal conductivity K1, and this one has a thermal conductivity K2, right? These are the things that are given to you. The two ends are maintained at two different temperatures. Now this end is maintained at a temperature, suppose T1, this is maintained at a temperature T2. First thing, what kind of combination is this? So you can very well see here that it is a parallel combination, because both the rods, although of different radius, one has a 2R, one has a R, same length, are connected between the same temperature differences, so they are in parallel. There is no loss of heat across the cylindrical surface. Again, there is no heat is being lost through this or this. Only way of conduction is along the length, the longitudinal transfer. Calculate the effective thermal conductivity of the system, where you have to find out what is the effective K of the system, right? How to find out this? Again, you can, as you have deciphered that this is a parallel combination, what you have to do is you have to apply that formula. Now, what is R1? R1 will be length is L1 by Ka1. So if I assume that this is of the length L, so it is L by K1 into area. What is the area of this small cylinder? It's simply pi r square. What is the resistance R2? It is again of the same length L, because both are of the same length, by K1. It's given here that it has value of K2, so this is K2. And what is the area of this second cylinder? Now see, this second cylinder is not the whole cylinder, it's only this cylinder of radius R2 minus radius R1. So what is the area of this? This will be pi 2r whole square minus pi r square. This is the area of this outer cylinder that is surrounding this cylinder of radius r. That means this is 3r square. So what you have is L by 3k1 pi r square, right? Now you have to find out the thermal conductivity of the system, effective thermal conductivity. Now what we know is that 1 by r is 1 by r1 plus 1 by r2. Let's put the values. 1 by r will be, I write this as, resistance is L by Ka1, so this becomes K into A is the area. What is the area of this whole system? The area of the whole system is pi into 2r whole square by, you have the length is L, is equal to 1 by r1. R1 is the value, you put this value here, what you have is K1 pi r square by L plus, this is K2, this is 3 pi r square by L. Let's see what are the things that are getting cancelled out. This L, pi will get cancelled out, and r square. What you have is, here you will have 4. So you have 4k is equal to K1 plus 3 K2. So if you look into the options, if you have any, yes, D is the correct option. So that's how it's solved when we have a series and parallel combinations. You simply use this formula for the resistance, put the values there, and you will get to the answer. So in this portion we have seen how we can apply the similarity with the electric currents in with the series and the parallel combinations even in thermal resistances. So stay tuned to Ask IITians for more on the other topics.